Kehoe Extrusion Modeling for Toughness is a material science engineering senior design project with team members David Abraham, Ken Gryc, Madi Kehoe, and Veronica. Our project sponsor is Helen Wycamp at Kehoe Aluminum. Kehoe is an aluminum billet supplier who provides UACJ, an automotive extrusion company, with specialized billets for their extrusion parts. To start this project, we were given 3 different 6000 series aluminum alloys, one 6082 and 2 6005A variants. We then used legal testing, a high temperature, high strain rate testing apparatus to create material files so that we could then simulate the extrusion behavior of these 3 alloys using Inspire Extrude. From there, we moved into a verification step where we actually extruded on campus using the Brita press and the M&M. And finally, the last portion of our project was focused on designing a homogenization for that 600529 alloy.
UACJ is seeking to use this simulation software to try and significantly reduce the production lead time from initial design to final product production. Currently, their R&D process takes around 4 years, a lot of that time being reruns of experiments to try and see where their breakout pressure is and where they can optimize their press performance. We're hoping that with the implementation of the extrusion modeling that we have helped create and the material files for the specialized alloys, it will be able to reduce that lead time down to around 2 years. The existing material data in softwares like Inspire Extrude only have very generic aluminum association standards such as a 6005 or a 6082 alloy, rather than having the specialized compositions that a billet supplier like Kehoe is able to produce. And we're using this simulation software to try and model the breakout force, exit temperature, and exit velocity of these alloys in extrusion conditions. Kehoe's specialized billets fall within the 6005A and 6082, and as you increase your silicon and magnesium concentration, you're going to be seeing increasing strength while also seeing a decrease in that extrudability. Which means if we're trying to optimize the extrudability of these alloys for UACJ, there are 2 things that we can alter, either the composition or the homogenization of these alloys. Kehoe would like to keep the same composition because they would like to see the same level of mechanical performance from these alloys, which means that we are looking at altering the homogenization. Homogenization is a thermal process that occurs between billet casting and extrusion to try and create a uniform microstructure for consistent extrudability. In our homogenization treatment, we're concerned about 2 main microstructural features: a magnesium silicon forming precipitate phase called magnesium silicide, and the dispersoids that form out of iron and manganese. As you decrease the homogenization temperature, the iron and manganese in solution decreases as you form more dispersoids, but if you drop it below the solvus line of the magnesium and silicon line, it will end up forming more magnesium silicide in solution, which you don't want for consistent extrudability. And that brings us to our hypothesis statement. That is, if 600529 undergoes a secondary homogenization step at 520 degrees Celsius, just above the 500 degrees Celsius solvus of magnesium silicide, then the extrusion breakout pressure will decrease because the manganese and iron in solution will decrease via the formation of dispersoids, while not forming any of that magnesium silicide.